All right, good morning and thank you for joining us. I'd like to welcome you all to Universal Sequencing Technologies semi-weekly webinar. This week we'll be discussing bioinformatics using TelSeq software analysis tools, going over some of the common problems that users discover and some of the solutions, tips and tricks for using the software and getting ideal results from your TelSeq data. With that, I'll go ahead and, let me go ahead and introduce myself. My name is David Nordell. I am the Inside Sales Manager for Universal Sequencing. And with that, I'll go ahead and hand it over to Peter to go ahead and introduce himself.
Good morning, David.
Good morning.
Okay, so my name is Peter Chang. I'm a senior scientist here at UST, and today we're going to talk about how we can look at the TEL read analysis and how you can use this information to assess the quality of your TelSeq library. However, before you really run this program, you first need to install the software and set up the genome references. So please visit our website at universalsequencing.com to download these programs and view other documentation as well as any videos that you may have, any videos that we may have. Once you've set up the software, you can run the program using syntax like this, which specifies the raw input, the output directory, and directories containing your genome database. You will also need to specify the sample barcodes to include in the analysis along with their respective genome references. For example, here, there are 8 different samples that should be analyzed using the HG38 reference. You may also choose to analyze different references for different samples in the same run. For example, here you have 4 samples from humans and 4 samples from mouse. If your run has only 1 sample, however, you may disregard the -S option, although you do need to specify a particular reference to use. When the TEL read analysis completes, your output will be contained in several files and directories. The full directory shown here will contain FASTQ files that you can use for phasing, de novo assembly, and any other downstream process. The output also contains a QC analysis report on the TelSeq data, and I will go over this directory and this file in the next few slides. The QC analysis report really breaks down into 3 types of analysis. One is on the sequencing quality and nucleotide composition. Another is an analysis of barcodes and reads in the run. And a third analysis looks at the molecular fragments and DNA input in the reaction. First part of the analysis really reports on the quality and composition of the nucleotide base calls for the 3 types of sequences, which we know are index 1, the molecular barcode, read 1, and read 2. The report describes the base quality across each position in the read from start to end. Here in this example, the base quality remains high throughout the read from the start all the way to the end. Oftentimes, however, it is normal for average quality to decline towards the end of the reads, but precipitous drops in base quality indicate an issue with the sequencing instrumentation. This is a cause for concern, and you should look into the sequencer to see if there are any issues that were reported. The analysis also reports on the average read quality for the read as a whole. Here on the left, most of the reads have high quality with Q scores of 37, whereas for the sample on the right, there's a subset of reads with lower read quality. Again, take a look at the report. Take a look at the sequencer for any issues that may arise. UST uses a barcode signature with specific nucleotides at positions 3, 6, 7, 12, 13, and 16 of the index. This analysis here shows that these base positions carry the nucleotides that we expect, and you should see this as well for all indices in your samples. The analysis also identifies overrepresented sequences. We usually expect some level of these sequences, but here they account for only 1 to 2% of reads, which is not really a cause for concern. Often if you have adaptive sequences or high amounts of technical contaminants, they will show up here, but any percentages under 2% is not a cause for concern. While the first section of the TEL read analysis sort of reports on the base quality and composition, the second section reports on barcode and read information, such as the total reads in the sample, the number of reads with total barcodes, and the number of unique barcodes. We anticipate some errors in the barcode sequences. Here you see that 4% of reads have an incorrect barcode. In general, for this particular report, there's 1 billion reads across 46 million barcodes. and only 4% of reads have an incorrect barcode, which is not a large number. Fortunately, the TellRead software is able to recognize and correct a lot of these errors. One thing you will notice is that of the 46 million barcodes, 30 million barcodes are associated with only one read. This is normal, and we expect that at high sequencing depth, sequencing errors will introduce these spurious barcodes. Most of the reads, 96% of reads, are associated with 10 million barcodes that contain at least 3 reads. What this means is that while there are a lot of barcodes, the bulk of the reads are found in these 10 million barcodes. Two important metrics here is the percent of reads with error barcodes and the number of reads per barcode. We typically report less than 5% of reads with incorrect barcodes, and we aim to have at least 15 reads per barcode. In this example here, there's 26 reads per barcode. If you run the TellRead analysis with multiple samples, you can compare these numbers across all samples. This is a good way to compare samples and to understand which libraries are performing well. In this particular case here, you see that the reads with wrong barcodes is only 2%, 2 to 3%, while the number of reads per barcode varies between 20 to 25, 26 number of reads per barcode. The last part of the TellRead analysis characterizes the quality of the input DNA. This is done by selecting 12,000 barcodes for each sample and mapping their reads onto their respective references. This way, you can get a good indication of the percent reads mapped. In this table here, the percent read is at least 98% reads mapped. The mapping of reads also allows us to understand the clustering of reads on the genome. One important property to pay attention to is the distribution of distances between the nearest alignments of the same barcode. This bimodal distribution can be used to gauge the quality of the linked reads. For example, look at this scenario here where you have a single barcode with 15 reads. As you can see, they're mapped to 2 different clusters on the genome. Reads can be either near, shown by these red arrows, these red distances, or really far from each other, shown by this particular blue arrow. Looking across all molecular barcodes, we can see that there are 2 types of distance distributions. Reads with 50,000 bases, reads within 50,000 bases are typically from the same original molecule, whereas reads with large distances are from different molecules. In some cases, we observe a shift to higher distances where the distal peak on the right is higher. This often indicates that the DNA to bead ratio is too high and that there are too many molecules per bead. Consider decreasing the amount of DNA or increasing the amount of beads in the library preparation. This scenario is one where the distal read dominates the distribution. Unfortunately, this is characteristic of a library without any linked read information, where reads from a single barcode map to random places across the genome. Again, if you run your TellRead analysis with multiple samples, you can compare these distributions across all samples to get an idea of which libraries are performing well. A good library should have a high linked read peak, along with a smaller distal read. Again, this is usually achieved with a proper DNA to TellRead ratio. For these 8 samples, 501 and 502 shown in the upper left have good distributions, while the others can be further optimized to reduce the amount of DNA per tell bead. You can also look at the insert size of these reads. Here you can see that 502 and 507 have longer insert sizes than the other libraries. The third part of the TellRead analysis looks into the clustering of map reads on the reference and uses this to estimate the size of the high molecular weight DNA on the bead. In particular, it defines the span of reads in a cluster as a super long fragment. In this example, there are 4 super long fragments. The length of all super long fragments greater than 4 kb are recorded and plotted. Here on the right, you can see the presence of super long fragments up to 200 kb in length. In this example, the average size of these super long fragments is about 50 kb, indicating the presence of high molecular weight DNA. You can also use the average size of all super long fragments, not only those greater than 4 kb, but all super long fragments as a measure of library quality. Clusters that contain only a few reads indicate those instances where only a portion of the molecule has been sequenced. This is often due to the presence of low molecular weight DNA, but can also arise from DNA damage or degradation as well as improper handling during the library preparation. We recommend aiming for average overall super long fragment lengths of at least 5 kb, with 8 kb is optimal to reduce the amount of low molecular weight DNA. When considering super long fragments of at least 4 kb, we also recommend aiming for average super long fragment lengths of at least 40 kb to maximize the amount of high molecular weight DNA. When running the tail-read analysis with multiple samples, you can compare these distributions across all samples to get an idea of which libraries are performing well. In this example here, the 4 samples at the top have higher quality, high molecular weight DNA than the lower 4 samples. The last analysis that we have is the number of super long fragments per barcode. Recall earlier that most barcodes have only 1 or 2 reads per barcode, and this translates to only 1 or 2 super long fragments per barcode. And in reality, the majority of data are found in beads that have at least 10 to 20 bark molecules per beads, and we usually target for 15 super long fragments per bead. Additional information is available at our website, universalsequencing.com. Please log into our website to view any documentation as well as any videos that we may have. We're also very excited to answer any questions you may have. Please feel free to email us at technicalsupport@universalsequencing.com.
Thank you so much, Peter. And with that, we'll go ahead and open it up to questions. If you do have any questions, please go ahead and type them in chat. And once again, thank you all for joining us. And just for your information, this webinar is being recorded, and a recording of it will be emailed out for you to view in case you joined late. So you will be able to watch it from the beginning as well.
Yeah, well, while we're waiting for the question, Peter, I have a question. I think in the example you showed, if people have reference genome, what if in the case for the de novo sample there's no reference? What will happen to the tail read?
Right. So if you do not have a reference genome for tail read, you can still run the tail read, but you need to specify a particular syntax without reference. However, when you run it without a reference, a lot of the reports is a lot of the mapping statistics and the calculation of super long fragments is not there. It merely report the number of barcodes and the number of reads we have. So you will still get a tail read report, but a lot of it will be different and truncated compared to the one with the reference.
Okay, and what's the reference information being used in the tail read? Will you also carry over to the downstream analysis? For example, tail sort or tail link?
No, tail sort and tail link and tail read really have independent usage of the reference. If you use a particular reference for tail read, it doesn't carry over to tail sort or tail link. The reference during tail read is only used to calculate metrics such as super long fragment lengths, the number of reads per molecule. It doesn't impact our ability to use those references for downstream analysis.
Okay.
So again, if you do not have a reference for tail read, you may still run the tail read program. But like I said, a lot of the metrics and statistics that are calculated that I described would not be available in the report because there's no reference. But it still will report to you the number of barcodes, the number of reads per barcode. It just will not calculate any metrics regarding the lengths of the molecules that you're putting on these beads.
Okay, thank you.
In many cases in which you do not have a reference, such as in de novo assembly, we recommend running tail read without a reference because the tail read report still will engage in barcode correction, adaptive trimming, and a lot of downstream analysis that is very useful for downstream analysis. So we do recommend running tail read even if you don't have a reference genome. You must run tail read. And then once you have a more proper genome using PacBio assembly or other technologies, or even through downstream de novo assembly, you can take those references and rerun tail read again to see if a lot of the parameters that I talked about, super long fragment length, the number of molecules per beads, whether they're proper or whether you see proper distributions with the reference that you generated.
Thank you. And I've also enabled the attendees to enable their mics if they'd like to ask a question verbally. Once again, chat, you can still use chat to ask your questions as well. All right, well, it doesn't look like we have too many questions coming in, and that was probably because that was such a fantastic presentation, Peter. Thank you. It was very in-depth. Okay, looks like we have one coming in. Just 1 second. Okay, what is the best way to see if the sample is good enough to sequence?
Okay, well, usually as I refer to, there are many metrics that allow us to understand whether a library actually is a linked read library or not. Oftentimes, we look at the number of reads per barcode. We look at the distal and linked read distributions. We look for particular ratios of the two kinds of distributions. We expect that most of the reads come from linked reads, and that is dominated by the distribution, the peak in the middle. We also expect and want another distribution, that represents distal read as well. So oftentimes when you want to know whether it's good for sampling, you would see whether your plots are following a linked read distribution. You also want to look at the number of molecules that you're putting on these beads as well. For bacteria and for humans, they require different kinds of numbers and different values. So depending on what your application is, you may want to look at these particular metrics.
Thank you. Looks like we may have a follow-up coming in. So just 1 moment. What if we see 2 peaks of the distribution chart? Should I redo sampling of the DNA?
Well, if we expect that there will be 2 peaks, and however, the only case that we are alarmed is that there is no peak for the linked read. Well, we usually want to aim for the distal peak to be slightly smaller, but it's okay for the 2 peaks to be of equal height. However, it is a problem if there is no linked read peaks at the left.
Yeah, so for that, quite often the reason is appears no, let's say it's a small linked read peak compared to distal reads. Quite often because there's a lot of short DNA fragment, which is kind of random distributed, so eventually all go to distal read. That's most likely indication that the input DNA quality is not good. So that seems if you pay attention on the super long fragment analysis table, you're going to also see that value indicate the same thing. So the distant read distant plot and closely related the output from super long fragment analysis table.
Thank you. And with that, I think we'll go ahead and start to wrap it up. Once again, if you have any additional questions, looks like we had one more come in. Is it the same way for metagenomic applications?
Peter, want me to it?
Yes, please.
Yeah. Let's go back to reference now. It's if. It's only if you know the reference, because for theory, the QC analysis it's important to have reference information, then we can align the reads, then we figure out what's going on there. For the metagenomic sample, quite often, truly we have no idea what it is. So there's no good reference. However, also quite often, E. coli is possible one of the things in the sample. So if you have no idea what it is, we just use E. coli as a artificial reference to do the mapping to see what we can get. Sometimes you can see if you have a good percentage, good number of reads mapping to E. coli, that will be suggesting probably indeed there's some E. coli DNA in the sample. In that case, you can get some indication from tail read analysis. However, sometimes the E. coli simply not even in the samples. So it's a tail read can only give you some high level information in terms of or the barcode error and or read count. Yeah, so that will be not too useful in terms of troubleshooting for the library prep.
So there's a question regarding the duplicates. Yes, in the table where we talk about the reads, the duplicate does refer to PCR duplicates. We know we have an unusually high number of duplicates, and that table refers to PCR duplicates.
All right. Well, thank you both once again, Tom and Peter, and thank you everyone for attending. We appreciate you joining us, and we hope that you can join us again in a couple weeks when we have another webinar. If you do have any questions, you can email Universal Sequencing, our tech team. Peter and Tom both will see those emails at technicalsupport@universalsequencing.com. I'll go ahead and email out that email address included with the video recording, so all of you will have access to both of those. Again, once again, thank you all for being here, and have a wonderful day.
Thank you.